Hi there. I'll discuss the proof of result about counting a number of trees. So the question is, how many trees can you construct out of n vertices? And the answer is given by the Cayley's formula. So let's say you have a number n, which is at least 2. Then the number of trees you can build out of n vertices is given by Tn is equal to n to the power n minus 2. Let's take a simple example where you have n is equal to 3 vertices. Now the number of ways you can construct a graph out of 3 vertices so that it is connected and actually minimally connected, which is the definition of tree, which basically says if you remove an edge, your graph disconnects. You can only construct one such graph, which I've shown here. Now, if you were to number the vertices in this graph, then you will end up having 3 different variants of this graph. And let's write those down. It's 1, 2, 3, and then it's 1, 3, 2, and the third one is 2, 1, 3. And so this number 3 is the result which is given by the Cayley's formula. So Cayley's formula counts the number of trees assuming that the vertices are numbered. Now before we jump into the proof, let me share some references. This proof was given by André Joyal, who's a professor of mathematics at the University of Quebec in Montreal. I've taken the proof from the lecture notes of MIT's 18.211, the edition taught by Professor Felix Gotti. This is a course on combinatorial analysis. I've also looked into the textbook prescribed for this course, which is called a Walk Through Combinatorics. I'll share links to both of these resources in the description to this video. Here's an outline of the proof. Say we want to find the size of set X, and say there is a set A whose size is known to us. If we are able to create a bijection F from A to X, and what it means is that every element in A has a unique image in X, and every element in X is the image of a unique element in A, then we can conclude that the size of set X is the same as the size of set A. This is the approach that our proof will follow. And for our purpose, set A will be a set of functions, and it will be a set of all functions from the set of numbers 1, 2, 3, 4 up till n to itself. Now I'll use the shorthand square brackets n to denote this set of numbers from 1 to n. Let's compute the size of the set A. So A is a set of functions, and let G be a function in A. Then G is a function from square bracket n to square bracket n. If K is an element in square bracket n, then it can be mapped in n different ways. Basically, it can be mapped to any number from 1 to n. And since we have n such k's to be mapped, the size of A is given by n times n times n times, and this multiplication goes for n times, which is n to the power n. Let's see a few examples of what this set A looks like, and I call it an here. Let n equal 3, and let g1 be a function from square bracket 3 to square bracket 3, and it maps 1 to 1, 2 to 2, 3 to 3. Let g2 be another function from square bracket 3 to itself, and let all elements of square bracket 3 be mapped to the element 1. Going back to our problem, we will construct a set Fn such that the size of this set Fn equals n squared times Tn, and Tn is the term we are interested in, which counts the number of trees. Then we'll show a bijection between An and Fn, and then using the fact that the size of An equals the size of Fn, we will prove the Cayley's formula. The set Fn is the set of all doubly rooted trees on n vertices. Next, we'll see what that means. Now let's look at what a doubly rooted tree is. Usually we would denote a vertex as the root. Now Cayley's formula doesn't care which vertex is denoted as the root, but for the purpose of creating this set Fn, we do care. Specifically, we will denote two vertices as roots. We'll call them root 1 and root 2, and we call this tree a doubly rooted tree. So now let's look at what the size of this set Fn is. So to create a doubly rooted tree, we first look at the number of ways in which we can create a tree on n vertices, which is given by Tn. Then we can choose root 1 in n ways, and then we can choose root 2 in n ways as well. Basically, it says that root 1 and root 2 can be the same. Let us recap where we are. So we have this set an, which is the set of all functions from square bracket n to itself. We know the size of this set is n to the power n. We have another set fn, which is the set of all doubly rooted trees on n vertices. And the size of this set is n squared times tn, where tn is the number of trees we can form on n vertices. And if we manage to show a bijection f from an to fn, then we can claim that the sizes of these sets are the same. And from that, we can derive the Cayley's formula, which is dn is equal to n to the power n minus 2. Now to show this bijection, for every function g in an, we need to map it to a unique doubly rooted tree t in fn. Okay, so what we're trying to do is there is a function g in an, and we are trying to map it to a unique doubly rooted tree in fn. Now let's take an example where n is equal to 4. So we have 4 vertices, and let g belong to a4, and let g be like this. So we have 1, 2, 3, 4, and then 1, 2, 3, 4 on the other side. So 1 goes to 2, 2 goes to 1, 3 goes to 2, and then 4 goes to itself. Now let's see what happens when we repeatedly apply g to an element in 1 to 4. So let's take the example of 1. So g1 is equal to 2 from the map. Then again applying g, we get g of 2, which is 1. Again, we get g of 1, which is 2. And then you get the gist. So there is this cyclical pattern. And what is happening is applying g to 1 leads us to 2. And then applying g to 2 leads us to 1. And these continue cycling. And so there's this cycle. Uh, we call a set of such elements, which are part of a cycle, C. And let's formally define it. So C is the set of all these small c's, such that there exists this whole number m, so that when we apply g m times to c, we get back to c. So now we've divided the set of vertices into those which are part of c, and in this example c will have 1, 2, and then 4. 4 because there is a self loop on 4. So applying g to 4 always leads us to 4. So the set of vertices is divided into this set C, and then a disjoint set, uh, which basically contains 3 in this case, because 3 is not part of any cycle. Okay, we'll look at two properties of these cycles, and then in about 100 seconds, we'll start constructing our tree. So the first one says for every element in C, the image of the element under G, which is GC, is also in C. Now, we can get some intuition with the help of an example. Let's n equal to 3, and let the cycle length also be 3. So we have 1 going to 2, going to 3, going to 1. Now you can see that if C is 1, then G of C is 2, which is a part of the cycle. And again, if C is 2, then G of C is again 3, which is also part of the cycle. And so this is the intuition behind this property. Now the second one says if you have C1 and C2, which are in C, then if the image of C1 and C2 is equal, that implies that C1 must equal C2. Now, there's a rigorous proof of this. If you need it, then put it in the comments and I'll supply it. But let's get some intuition. So let's say we have a C1 and C2, and then their image is equal. So G of C1 is equal to G of C2. And let's say this is some C3, which is also in our set C. So repetitive applications of G to C3 can only bring it back to C3 if C1 equals C2, because otherwise we'll have two paths. Finally, we can start constructing our doubly rooted tree corresponding to an element G in AN. So recall that G induces the cycle set C, and then there are vertices which are not in C. So we'll first take look at the numbers inside C and see how we can fit them into a doubly rooted tree. So let's say the size of the set C is K. Then sort the K elements of this set and let's call them C1 to Ck. Now the simple scheme to construct our graph is to have G of C1 as the first vertex in the graph, and then G of C2, add an edge between G of C1 and G of C2, and so on until you reach G of Ck. Now recall from property 1 in the previous section that G of Ci also belongs to the set C. Now let's designate G of C1 as root 1 and G of Ck as root 2. Now the question is this connected? As in, if I have to find a path between Ci and Cj, G of Ci and G of Cj, because those are the nodes in this graph, then what do? And the answer is simple. You just go from G of Ci to G of Ci plus 1, and so on to G of Cj minus 1, and then G of Cj. But that just proves that this graph is connected. Uh, the next question is, are there any cycles in this graph? And this is a slightly tricky question. Uh, what this basically means is G of Ci equal to G of Cj for some I and j. Because if that's the case, then you'll have G of Ci, some vertex somewhere in this graph, and then it'll connect to G of Cj minus 1. But G of Cj minus 1 has to connect to G of Cj, which is actually equal to G of Ci, and so you have a cycle. And the answer is simple. So using property 2 that we discussed in the previous section, if Ci and Cj are two elements of the set C and their image under G is equal, uh, which is to say that G of Ci equals G of Cj, then that implies that Ci must equal Cj. And so that resolves the question that there are no cycles. And this path from G of C1 to G of Ck without any cycles is a tree. Let's construct an example tree, and let's take an example where all vertices are part of some cycle under G. So let's write down G. So it's n equal to 5, 1, 2, 3, 4, 5, and on the other side. And then let's create two cycles, 1, 2, 3, and then 4, 5. Now the set C is a square bracket 5, which is 1, 2, 3, 4, 5, and then there is no other vertex outside the set C. Now let's sort the elements of C, and it's just simple 1, 2, 3, 4, 5 again, and let's write their image under G. So G1 is 2 and G2 is 3 and so on. And so these will be the vertices of our doubly rooted tree. Let's connect all of them by edges, and then let's designate uh, G of C1 as root 1 and G of C5 as root 2. Now, is the doubly rooted tree we created unique to G, or does there exist some other function h which is not equal to G which also maps to this doubly rooted tree? Now, h doesn't equal G just means that there exists some p in 1 to 5 so that the image under h is not equal to the image under G. Now, this is simple to check. Remember that we are only considering the case where each vertex is part of some cycle under G. So let's write the vertices C1 to Ck. In this case, K is equal to 5. And then in sorted order, these are just 1, 2, 3, 4, 5. Now, the doubly rooted tree corresponding to G is image of 1, image of 2, and so on, an image of 5. And the one corresponding to h is h of 1, h of 2, and then h of 5. But since this is the same doubly rooted tree, each of these positions are actually equal, and this means that h is actually equal to g. Now what this means is that if every vertex is part of some cycle under G, then we can uniquely map G to a doubly rooted tree. So we've created a doubly rooted tree out of all vertices which are part of some cycle under G. Now let's look at vertices which are not part of any cycle under G. Uh, Let G be like this. So we have a cycle 1, 2. So C is 1, 2. And then we have the element 3, which is not part of any cycle under 3. So how do we connect such vertices to the doubly rooted tree we've created so far? So what we'll do is we'll draw an edge between a vertex V in the set and its image under G. And let's see what this graph looks like for this example. So in this case, C is equal to 1, 2, and then we can create this path doubly rooted tree out of C. So it just has two vertices, 2 and 1, where 2 is root 1, 1 is root 2. And now let's look at the only other vertex, which is 3. So what we'll do is we'll draw an edge between 3 and G of 3, which is 2. So to recap, we'll connect the vertex 3, which is not part of any cycle under G, to its image under G, which in this case is G of 3, which is 2. Two things we still need to make sure of are that this process results in a connected graph, and second, there are no cycles in this graph. We'll take another example of this graph construction, and then we'll check those two properties. Here's another example, and we want this function g to correspond to a unique doubly rooted tree T in f of n. So let's start with elements which are part of a cycle under G. And so those are, in this case, 1, 2, and 3. And they're already in sorted order. So let's create a path tree out of this. So we start with G1, which is 2, then G2, which is 3, and then G3, which is 1. And then we add edges in between. And then we designate the first vertex as root 1 and the last vertex as root 2. Now let's look at elements which were not part of any cycle under G, and those will be 4 and 5. So we start with 4 and then create an edge between 4 and G of 4, which is 3. Then we create an edge between 5 and G of 5, which is 4. And this is the doubly rooted graph which we want to correspond to G. And if F is the bijection we were trying to form, then F of G equals T. Note that I'm still calling it a graph because we haven't proved that after the addition of 4 and 5, this is still a doubly rooted tree, which we will do in the next few seconds. So let's make sure that the graph that we've constructed is indeed connected. So first, let's consider the vertices which are part of a cycle under the function g. And so let those vertices be C1 to Ck in sorted order. And we've seen how to create a graph out of these vertices. So GC1 is root 1, and then GC2 and so on until GCK, which is root 2. And we've established that all of these values G of Ci's are distinct, and they are connected along a path, straight path. So this is indeed a connected structure, and it's a doubly rooted tree. Now let's consider vertices which were not part of any cycle under G, and let V be one such vertex. So the way we are constructing a graph out of this is we are adding an edge between V and the image of V under G, which is G of V. Now we want to show that this vertex V is somehow connected to the path we've established in part 1, which is GC1 to GCK. So for that, one property which will come handy is this one. So for every such V, there exists a number M such that M repetitive applications of G to V, so GMV, belongs to the set C. So in other words, GMV is actually one of the vertices along that path from part 1. Now this is easy to prove. So let's consider this series V, G of V, G2 of V, G3 of V, and so on, Gn of V, where n is the total number of vertices, Gn plus 1 of V. Now we only have n distinct vertices, so at some point uh, this series has to start repeating itself. So which means that there has to be some index m such that, and some other index p which is greater than m, such that Gm of V is the same as Gp of V. And we know when this happens, this means that a GMV belongs to the set C, which is what we set out to prove in this property. Now, how do we use this property to show that V is connected to the path from part 1? Now, let's start with V and add an edge to GV, as is the design of this proof. Now, there are two cases. Either GV itself belongs to C, in which case we are done. We've shown that V is connected to the path, or GV is not connected to C, in which case we will add an edge from GV to G of GV, which is G2V. And we'll keep on doing this, and we'll keep on encountering these two cases until we reach an index M, such that GMV actually belongs to C. And this comes from the property we proved above. And so this establishes that V is indeed connected to the path. We've established that the graph that we constructed is indeed a connected graph. Now we need to establish that there are no cycles in it, and then we can conclude that it's a tree. So let's consider the case of the path we created from all the vertices which are part of some cycle under G. We've established before in the video that there is no cycle on this path, and this is indeed a tree on its own. So now let's consider the vertices which are not part of any cycle under G. And the first thing to consider is that there cannot be any cycle which contains only vertices from this set. Because if that's the case, and let's say that cycle is V1, V2, Vp, and then it cycles back to V1, then all of these VIs, V1 to Vp, will actually be in C, because that's the definition of how we created the set C. So this is clearly not the case. And so any cycle containing vertices from uh, V slash C has to contain some vertex from the set C as well. So now let's consider this path again, GC1, GC2 to GCK. And let's say that there is a cycle which contains some vertices from V slash C, and which also contains these two vertices from this path. And these two vertices can be the same as well, so it can only be one vertex. So from the first property that we proved above, we know that there has to be at least one vertex from C in this cycle. Now let's label these two vertices on the path W1 and WL. So our construction of this graph says that we will draw an edge between VL and G of VL. So this means that G of VL is equal to WL. And so continuing this logic, we know that G of VL minus 1 is equal to VL, and so on. And then finally, G of V1 is actually equal to V2. But, and here is the contradiction. Looking at this diagram, you also know that when you connected V1 to the path, you drew an edge between V1 and G of V1. So G of V1 is actually W1. Now, both of these cannot be simultaneously true because clearly V2 does not belong to C and V1 belongs to C, and this is a contradiction. And what this says is that any cycle can only contain vertices from this path, which we already know has no cycles. Okay, so we are at the final leg of this proof where we show that f is a bijection. Recall that f is a function from the set an to the set fn. Now an is the set of all functions from square bracket n to square bracket n, and fn is the set of doubly rooted trees. So it'll help to look at this bijection proof visually first. So to show that f is a bijection, we need to show two things which are necessary and which suffice. So the first thing is that if there are two functions g1 and g2 in an such that the image under f of each of those, and the image is basically a doubly rooted tree in fn, if the image is the same, then g1 and g2 have to be same. So let's look at this visually. So this is the set an, each point is a function g. So we have two functions g1 and g2, and then this is the set of doubly rooted trees, and t1 is a tree, doubly rooted tree, and so is t2. So what this condition says is if both g1 and g2 produce the same tree t1 under f, then g1 has to be equal to g2. And the second condition to prove that f is a bijection is that for every doubly rooted tree ti in fn, there exists a function gi in an such that if we follow the process of creating a doubly rooted tree from gi, we'll end up with ti. So the image of gi under f equals ti. And if these two conditions are met, then we can conclude that f is a bijection, and then that proves the Cayley's formula because we can say that size of set an is equal to the size of set fn. Let's prove the first condition, which says that if g1 and g2 map to the same doubly rooted tree, then they must be equal. So here I have a portion of the doubly rooted tree, and it has root 1 and root 2, and then there is a unique path between them because it's a tree. And then we know that the set C, it's basically V1 to Vk sorted, which I've written as C1 to Ck. And we know that while creating the tree, G1 mapped Ci to Vi, and then G2 also mapped Ci to Vi. And what this tells us is that G1 Ci is equal to G2 Ci for all such Ci's in C. I mean, this is something we've shown earlier in the video as well. Now, the proof for the other vertices is similar. So let's say Ui belongs to set of all vertices V except for those in C. Now, these UIs are connected to this path V1 to Vk. And let's look at one branch which is of length L. So it starts from U1 and then goes to UL and then connects to the path. Now, through the construction process, we know that G1 will map U1. It will create an edge between U1 and G1 of U1. And similarly, G2 would have created an edge between U1 and G2 of U1. But since this doubly rooted tree is the same, we know that G1 of U1 is U2 and G2 of U1 is also U2. And so we can say that both G1 and G2 are the same for all UIs in V slash C. And so from the union of these two results, we can conclude that G1 equals G2. Let's prove the final condition, which says that for all doubly rooted trees in Fn, there exists a gi in an such that when we apply f to gi, and applying f basically means following the tree creation process that we've discussed earlier, we get this doubly rooted tree ti. So basically we have to find a function gi from square bracket n to square bracket n. And here I have a portion of ti with the two roots shown as v1 and vk and a unique path between them. Unique because this is a tree. Now again, let C1 to CK be the VI is written in sorted order. And what we'll do is we'll map GI of CI to VI. And we'll do this for all CIs on this path C. Next, we'll look at vertices which are not on the path. Since this is a tree, they are connected to the path. And let's show one such branch where we have UI plus 1, then UI, and then the leaf is U1. And let's map GI of UI to UI plus 1, which is basically the immediately next vertex on UI's path to this V1 to VK big path. You can see that we've kind of reverse engineered the doubly rooted tree creation process from G, and basically f of gi is equal to ti. So if we were to create a tree out of gi, we'll get ti. I haven't given a rigorous proof, but let me know and I'll provide one. All right, so we're done. We've shown that f is a bijection, and then we can derive the Cayley's formula as discussed earlier in the video. This concludes this video. I've tried to present one of the known proofs of Cayley's formula. I've tried to expand quite a bit on a number of steps mentioned by various authors in my references for this proof. Uh, in making this video, it was a reality test of my own understanding of this subject, and I must say that my understanding improved quite a bit through making of this video. If there are any holes, let me know in the comments and I'll try to plug them. I am pretty positive that this will only get better with time. Thank you.